So now we've got Ahlam, who originally did her studies in Saudi Arabia and did a gap year in the US before going back to teach in Saudi Arabia, and now here she is doing a PhD with Nikolai and Tim, and yeah, she's going to talk to us about fractional viscoelastic models today. Over to you.
Thank you for coming. I will talk about the fractional viscoelastic models.
And you play that right there?
Yeah.
No.
Yeah, is there a way to go into like a presenter view on here? There's one of these things.
Arrows.
Yeah. Okay. Yeah.
I'm gonna throw the outlines for the topics that I will cover today. The first one is fractional viscoelastic model. Then I will talk about Taylor-Court flow problem. Then I will show the numerical approximation and scheme that I used, and then show some of numerical results, then future work. Here I will give overview of fractional viscoelastic model. The most elementary model for the constitutive response of viscoelastic fluid was proposed by Maxwell. Elementary models can be generalized using fractional derivative to describe the behavior of viscoelastic materials by replacing the ordinary derivative with the objective fractional derivatives of strain and stress. The fractional derivative constitutive model can be extended to include the finite deformation. In fractional viscoelastic models, a fractional dashboard is proposed to describe the dependence of the viscous response on deformation history, while elastic spring is used to represent a time-independent elastic response. Fractional models with few parameters, such as a fractional Maxwell model and upper convective Maxwell model, have the theoretical advantage of being able to describe a wide range of complicated combination of conventional springs and dashboards, which would be difficult to achieve with regular spring and dashboard structures. Also, fractional models can predict wide variety of dynamical behavior with only one or two additional fractional orders, making them ideal tools for analyzing the behavior of viscoelastic materials. Here, I'm working on Taylor-Court flow problem. This type of flow has the particular importance of allowing the rheological characterization of materials by loading the unknown material into the gap, annular gap, rotating one cylinder in a steady or unsteady motion, and measuring the resulting torque in the second cylinder surface. Consider the unsteady unidirectional flow for fractional viscoelastic fluid inside real concentric cylinder rheometer, which is annular flow. Here is the eccentric cylinder geometry, with eccentric in our case is equal to 0, and here the annular geometry and flow. The governing equations in terms of velocity and shear stress for fractional Maxwell model are given by these equations. The first one calculate the velocity, and the second one calculate the stress. And we have the boundary condition, which is calculate the values for velocity in the boundaries of cylinder, which is indifferent here. And we have the initial condition are given by this equation. To solve these equations, we employ the spectral methods to solve this system of differential equation. that covering the study or study flow of fractional viscoelastic fluid in angular geometry. We choose the spectral method because they are global methods, and the discrete equation generated involve a relationship between the unknown that are not necessarily local. The major advantage of spectral method over the other methods of discretization is that they can generate high-order approximation to the solution of differential equation. We apply the spectral by inserting the spectral approximation for the Garkin method and basis Lagrange method functions in the weak formulation of the previous equations to obtain the discretized equations. This is the discretization equation for velocity, where here we have different parameters from the discrete of time derivative, and we have D is the spectral differential matrix, W is the weight function, and we discretize the boundary condition for the velocity. When we get the values for U, we can calculate the equations for stress. To prove the validation for the proposed method, I was developed numerical code with MATLAB to solve these equations, and I tried a couple of examples. Just show one of them to just prove the agreements between the result that I have with that obtained by finite difference in another paper that's published by Farias in 2018. And here, this is the examples. We have source terms and the exact solution here. And the boundary condition was zeros in the boundary. I calculate the L2 norm error, and as shown in the first plot, there is an influence of L2 with on N, and we have the exact or a good agreement between the exact and approximate solution for N equal to 12. Here, to prove the accuracy of the proposed method, I calculate the max error, and as we see here, we have decreased max error with increasing of the values of the spatial error N. And this caused the convergence. This caused the convergence of velocity that's equal approximately 24 in space. And here in the last column, we have three values of order of convergence for 3 pairs of N. For specific discretization and fluid parameters, we study the evaluation of normalized velocity and stress component at some regions between two rotating cylinders. In the Newton fluid, we have the higher velocity near the outer cylinder, which is at R equal to 1. This is because the outer cylinders rotate faster than the inner cylinder, and the same for the stress. For viscoelastic fluid, as we know, the relaxation time plays an important role in the viscoelastic fluid. we noticed that a slow momentum transfer from the wall to the fluid when comparing with the Newtonian fluid. The variation stress with time is more smooth when compared with Newtonian fluid. Especially when the outer cylinder starts rotating. For special case when R bar equal to 0.5 in the middle, here, we notice the slow response of the fluid because this region is far away from the both rotating cylinder. Another experiment that I have do is the step strain experiment, which the outer cylinder suddenly stopped after a period of time, and this will be removed from position A to B. And we here have a different values of deformation, and we have different levels of refinement, and we have a normalized delay time. During this sudden strain motion, we measure the evaluation of normalized shear stress at particular point R bar equal to 0.25. And in the first plot, we have 3 levels of refinement, and we apply deformation equal to 100%. And we show that, and as we see, as psi goes to 0, this means the outer cylinder rotates faster than the inner. The outer cylinder has to rotate faster to attain the fixed distance, attained in progressive shorter period of time. In the figure 2, we show the evaluation of deformation. The second plot, we show the evaluation of deformation with time for 3 different levels of refinement. For 3 different tangential velocity imposed in the outer cylinders, as expected, with a progressive increased rotational velocity, a higher approximate of the cross-step strain displacement is obtained. In the third plot, we show the normalized shear stress for 3 levels of deformation, of imposed deformation, and the fourth plot is just zoomed view for the stress relaxation for the smaller value of deformation. We conclude that the numerical code is powerful and can be used in prediction of real fluid behavior modeled by fractional viscoelastic fluid. Here in the last figure, also we can show the power of fall of fractional model for the case where different fractional exponent here for the value of beta. We see that for small value of beta, we have the small peak of the stress, the blue one, and it takes a long time to relax. While the large value of beta make the peak of stress is larger and take a little time to relax. And then I have studied the generalization of fractional Maxwell model. The first theorem that was in paper that published by Young 2010. I just derived the exact solution for that based on the green function that solved by Laplace transform method, which was in Young solved by derived by Fourier transform method, and we get this form for the solution. Another theorem, we generalized the last theorem by adding a new term, this alpha 2, and also derived the solution for this equation based on the green function that's solved by Laplace transform method. The future work, I will extend the numerical analysis of the quote problem to the case where there are two fractional time derivatives on the left-hand side of radial momentum equation for the quote flow between rotating cylinders. Following the derivation of new fractional Viscoelastic model, analyze these models in terms of their rheological behavior and derive exact solution if possible. Perform numerical simulation using the new models and compare their predictive properties for different models and material parameters. The last thing is perform comparison with relevant experimental data. And here are some references if you are interested. And that's it. Thank you for your time.
Excellent. Thank you, Ahlam. Any questions?
Where do you get your experiment?
Sorry?
You said that you're hoping to compare with experiments. Where would you get the experimental data from?
From various paper.
From literature.
Yeah.
Related question, and what is the practical, what are the practical implications of your research? Is there some kind of industrial liquid material that these the materials you are modeling are found? To rephrase my sentence, but I'm just asking, are there applications for what you're doing in industry, or you said there are experiments, but why are they doing these experiments?
Because
Materials characterization.
Yeah.
I know, but I mean, for which use?
Yeah, which common materials are behaving like these fractional Maxwell models? Is it like lubricants and things?
Lubricants are polymeric materials.
Polymeric lubricants. Yeah, along the similar lines then, I mean, you said you're going to add multiple fractional time derivatives. They're with different kind of scalings, and different orders, right?
Mm-hmm.
That's an idea for future work. Is this to represent materials that have multiple relaxation processes?
Yeah.
Yeah. Oh, okay. So, yeah, I mean, would there be mixtures then, or would a single? Do you think a single material would have this property, or would it be mainly mixtures? And so, in your solution so far, you've looked at different speeds of the cylinders relative to one another, and you're finding these like plateaus when the speed is increasing, right? I mean, it looked like you were, at least within the Newtonian regime, staying in this kind of more laminar flow. But are there similar instabilities and transitions, do you think, if you keep increasing the velocity like there is in Newtonian?
To think about it.
It'd be interesting to like compare them, kind of stability as well.
Last time someone was presenting about reversing the clip burden. It would be interesting to see like the time dependence.
Yeah, because
When
you
you
just have this
rotate one way
linear.
and then the other
Yeah.
way.
At the minute, you've got a linearly increasing velocity, right? You could do other things and reverse it, and maybe have a quadratic or something.
Yeah.
So it's linear at early times and linear at late times, but in the opposite direction. Yeah, looks like you've got a fun sandbox to play with.
The models that she's looking at are only valid in the linear viscoelastic regime.
Yeah.
To look to add more
Oh,
complications in the nonlinear regime.
yeah. I was thinking more like with the experiments. Excellent. Okay, well, thank Ahlam again.